Hello everyone, good morning. I think everyone is fresh and in a few minutes we can start our second session. I have Akash with me here.
Hello everyone, hope you are doing good. Um, we'll just wait another couple of minutes for the rest of the audience to join in. I hope the voice is clear and audible enough.
So, can you please share how was your experience with using Monk and uh, how it helped you create applications, the tutorials that you tried? Any comments on them? Any suggestions? Please comment the same.
All right, let's begin. Um, so let me continue where we left off yesterday, quickly recapping the contents that we did. So yesterday, Abhishek took a brief introduction about the topic of image processing and computer vision, how different applications, both earlier and now, are being developed in this domain. What are some of the challenges and bottlenecks working as a developer in this industry, and how we came up with MonkAI and set of offerings and the tools available. MonkAI, like Abhishek described yesterday too, MonkAI currently has three offerings, three primary offerings. First being a transfer learning based image classification toolkit. Second, simplified low code object detection workflows. And lastly, a point and click interface for building computer vision models, a GUI based approach to deep learning for computer vision. All these three tools are open sourced and available on GitHub. So you can start using them in your projects from day one. Apart from that, we keep on building a lot of collateral, a lot of study material for entry level developers who are just getting acquainted to the topic. Um, so if you go on GitHub and check out monk underscore v1 repository, there is a directory called study roadmaps. Within the study roadmaps, we have divided the roadmaps into different sections depending on the complexity and the user level. So there is a getting started roadmap that introduces you to what Monk is, what it has to offer, and how you can use Monk in your computer vision applications. The second is a transfer learning roadmap that pretty much evaluates how different options and different parameters of Monk can be applied and updated when working with computer vision applications, and how different hyperparameters and parameters available within Monk affect your computer vision project. Um, Next, we also have for total beginners to the topic of image processing and computer vision, we have an image processing basics roadmap wherein you get to learn some of the basics of image processing, the mathematical operations required, and how to program them or write the mathematics into code of image processing, or rather digital image processing. Alongside the image processing roadmap, we also have some deep learning building blocks that are very state of the art and also utilized widely, far and wide, by deep learning researchers in the domain of computer vision. We'll look at some of these building blocks and how you can utilize them for building your image classification project. Like I mentioned, apart from the image classification transfer learning toolkit, we also have low code syntax invariant object detection workflows. Now, if you look at these low code workflows for object detection, within object detection itself, uh, the major hassle being there is no standard data annotation format. I mean, there are widely used and popular annotation formats like Coco, Pascal, VOC. However, a lot of annotation tools also allow you to export annotation in these formats. However, more often than not, juggling between these formats becomes a hassle. So all these low-code workflows come with their own data ingestion platforms, data ingestion formats, along with our own annotation format, which is pretty similar to YOLO. And we also have scripts and tools available to convert from one data format to another, so that you can use them quickly. So as you can see, again, we have maintained a low-code syntax wherein with just 4 lines of code, you can begin your object detection training. We'll go over some of these. Abhishek will go over some of these in the second half of today's webinar. And lastly, we have a point and click interface for carrying out deep learning for computer vision. The point and click interface is built on top of PyQt, a UI development library of Python. And the entire suite of programmatic access that we provide with MonkAI's low-code syntax is accessible with the GUI. It's just that it's a point and click button interface, and so the UI also has some default recommendations. So when you load up a project or load up a data set, it suggests certain default parameters and default hyperparameter values that you can move along with. However, you are always open to play around with them and see if you can improve accuracies one way or another. All right, I hope you got the gist of today's events. Let's in fact resume with where we left off yesterday. All right. So what we'll do is we'll start out by quickly going through our training exercise, building an image classifier, just a recap of the steps that go into building an image classification system using Monk. And then we'll quickly recap the elemental features and move on to some of the core features and available hyperparameter update options. Now, if you want to follow along and code with me, you can open these notebooks in Colab. There is an open in Colab button. When you do so, just ensure that the runtime on Colab is set to GPU. I'll quickly just go over how you can do that. All right. So step one would be save a copy in your own drive so that you have a copy of this notebook later on to work with. In fact, from the audience, I would request you to choose different backends and explore with either Pytorch or Keras. I'm using the Mxnet version of the notebook, and we'll sync in at the end of the notebook how all of our results went. All right, so each of our notebooks within the study roadmap section is divided into smaller sections like these, wherein we have taken sure that each of the notebooks are independent and you do not have to go back to check the documentation or revisit the documentation. So each of the notebooks has its own setup instruction. Yesterday during the webinar, I believe a lot of audience members reported that they were facing hassles with some setup errors. We updated our notebooks to ensure that setup is enabled for Colab and not Ubuntu. So I hope this will work directly. So while we are setting up Monk, let's just check out some of the elemental features that are there. Now, let's look into the acceptable data types that Monk takes in, specifically for image classification. Now, I'm sure a lot of the audience members who has attempted image classification, at least once, understands the data format in which image classification systems ingest images. So, which is either in a foldered manner. So to explain, suppose your data set has two classes, cats and dogs. So your data set would have two folders, namely cats and dogs, with the cats folder storing cat images and dogs folder storing dog images, so on and so forth. So if you have n classes, you would have n folders storing n classes of images. something like this, right? And to ingest this, right after creating a project, all you have to do is pass the path to this images folder. So pass the path to the parent directory. Along with setting the dataset path, you also choose the neural network architecture that you want to utilize and the number of epochs. Now, for this example, we just have training data. Monk also allows you to ingest validation and test sets along with the training data. We'll look into how that happens. Apart from the folder data structure, Monk also takes CSV labeled data sets, wherein the dataset structure is something like this. You have a train folder within the parent directory, which stores all the images within your dataset. And you have a train labels.csv or any CSV file with just two columns, one storing the ID or the file name and the second storing the labels. Now, right now, this is not multi-label, this is single label classification. We are actively working towards integrating multi-label classification, and you'll see multi-label classification pretty soon. So those are the two data types for image classification that are accepted by Monk for transfer learning. I hope all of you were successful in setting up Monk on Colab. In case you had any issues, do post in the comments and someone from the team will get back. The next step is importing the library. So for our case, we are using the Keras backend. You could be using Pytorch or Gluon, and you would see the same in the import statement. Right. So the getting started notebooks and the quick prototyping mode are kind of similar. So quick prototyping mode is for beginner level developers who are just getting introduced to the field, so they do not get overwhelmed with the number of options or the number of hyperparameters that they have to tune. The quick prototyping mode is pretty straightforward, in which you just have to import the library. You set up your project and experiment. You pass in the data set and the number of epochs you want to train. You can, in fact, also list the available pre-trained models that out of which all contain state-of-the-art deep learning models, and you can choose either of or any of them in your image classification training. And once you've chosen one of the deep learning neural network architectures, you can begin training, which is just a 5-step process. So even if you do not understand a lot about how deep the deep learning algorithms function in the background, or how gradient descent or backpropagation works, you can still churn out some computer vision models and load the models in inference mode and evaluate and test your computer vision model on test images. So right now we looked at some of the supported data types and supported data sets within Monk. Next, we'll move on to some of the parameters that are available within Monk that can be tuned and tweaked by developers to achieve better performances and manage their projects better. So there are 4 types of parameters available or accessible to the developers via MonkAI. Namely the model parameters, data parameters, training, and the hyperparameters. We'll go over what are these and how can they be updated individually. So let's check out some of the model parameters that are available. Now, the model parameters pretty much control how you want to modify the chosen network. So this happens after you've chosen a pre-trained neural network architecture. So for example, after you've chosen a resnet or an inception or a densenet block that you want to train further, these options come into picture right after that step. So step one is whether you want to utilize CPU or GPU for your model training process. In case you do not have access to GPU, MonkAI by default checks if you have a GPU option and by default is set to use a GPU. However, if in case you do not have a GPU accessible either locally or on the servers that you are processing, you can right after setting up your data set and before training, set your project to not use a GPU. So right after you've chosen, set your dataset path, chosen a pre-trained model, you can set your project to not utilize a GPU. However, after updating some of the model parameters and some of the other parameters, you would have to do a reload of the project so that all these state flags are saved in the system. And after setting this flag to false, you can begin training as normal. It's just that training with CPU takes a bit longer time as compared to GPUs, of course. The second model parameter that is available to users is whether to use, pre-trained weights available with the resnet or inception block. So all these pre-trained models available within the MonkAI library, or in fact available within any of the libraries or frameworks, have actually been pre-trained on some large-scale data set and carry their own sets of weights and biases. And these models have usually been trained on a large set of classes, so they know about a lot of objects, a lot of images, and a lot of patterns already. Though not specifically any set of objects, but in a broad and general sense, they know about most of the objects that are available in general imagery. With transfer learning, our primary goal being we are trying to tune this model to classify or or determine what the image holds specifically. So, for example, in our case or in our example, if we want to build a cat versus dog classifier, what we are trying to tune the classifier is to specifically the purpose of cat versus dog classifier. Now, the model earlier might have been able to distinguish between cats and dogs. However, we are trying to enhance its performance on just cats and dogs imagery. And that's something that we try and achieve with transfer learning. Now, when we try and do so, we can either use the pre-trained weights, right, that are already available to us, or we can do another thing. We can randomly initialize weights and biases within the neural network architecture. Let's check out how we can do so. So right after you create your experiment and the step where you load the dataset and choose a base neural network architecture, you set the pre-trained weights to be frozen. And what this does is it trains a final last layer in the neural network that is trained to specifically determine whether the final image is of a cat or a dog. However, you can also randomly initialize the weights in the neural network. So you can set update use pre-trained to false, this flag to false, and reload the experiment. And what this will do is this will randomly initialize the model weights and biases before training. We'll look at how this affects the training process and how this affects accuracy soon. However, just letting all of you know that these are some of the flags available that you can tweak and play around with. We've also compared experiments. So if you see using pre-trained weights versus randomly initializing weights, there is a minor drop in accuracy. However, this might not always be the case, and this is something that depends on a case-to-case basis. let's come back to the notebook, the experiment that we were building. Now that our library has been imported, let's create a sample project and also name our experiment and create a project. Now, creating a project, what this does is wherever in your current active working directory, it creates a workspace folder. Within your workspace folder, what your workspace folder primarily holds is all your projects, all your comparisons, and all your logs. So that any of your experiments that you have been creating and building are logged, and you can keep a track of everything. Now within your project, you can have multiple experiments. So this is this experiment 1 that we built. So within your workspace folder, we would have a project folder, and within each project folder, you can have multiple such experiments. Within each experiment folder, also there is an output folder that contains logs. Logs as in loss curves, accuracy plots, GPU training times and benchmarks available, and your final trained models are also available in the output directory within the experiment folder. Also, just to mention, the summary that you see is stored within the experiment state JSON file. So whenever you try and print the experiment summary, it is retrieved from this file. All right, like I mentioned, the quick mode training is for beginners who are just getting introduced to how a deep learning workflow works and how image classification models can be built. There are 3 steps. You put in the dataset path, you put in the model name that you want to utilize, and you set the number of epochs you want to train for. Like we just discussed, the dataset structure here is we are using folder dataset with each class or each folder storing its own class of images. So a cats folder storing cat imagery and a dogs folder storing dogs imagery. Now, right after creating our experiment, we begin with loading the dataset. So what we do is run the default function and pass in the dataset path, which is located here. We choose a neural network architecture. Now here we've chosen a resnet 50. We can find out a list of available models, pre-trained models, using the list models function. So the Keras backend has these pre-trained neural networks available to us, and we can choose any of them. In fact, let's modify the notebook to use something else. I'll choose Instant. You can choose, if any of the audience members is following along and running this on Colab, you can choose any of the pre-trained neural networks. I've set this to be trained for 5 epochs, and we start by preparing the notebook. So it seems Colab uses TensorFlow 2. What we'll do is we'll quickly downgrade our TensorFlow. And reinstall TensorFlow for version 1.14. Or I guess we can do that by just restarting the kernel. So in case you're modifying any of the dependencies on Colab, you would have to reload the notebook once. All right, meanwhile, let's get back to our study roadmap and the model parameters that we were looking at. Now, till now, we saw the CPU, GPU flag and the pre-trained versus random initialization of weights. We also have frozen and unfrozen networks. Let's look at what that means and how that would help. So freezing or unfreezing a base network, what this pretty much means is that at the step where we choose a pre-trained model, so for example, in this case, we are using a ResNet 18 neural network. So like I described, the ResNet architecture would come with its own pre-trained set of weights and biases. So during transfer learning, you have two available options. You either can train the existing set of weights and biases along with the final layer of transfer learning that you are trying to achieve, or you can choose to keep the pre-trained model frozen and just train the final layer. That's all that freezing or unfreezing means. So if you set freeze-based network to true, then the pre-trained model would, the pre-trained weights and biases would not be modified. They would kept as it is, and only the final layer weights and biases would be learned by during the training process. However, you can also set the model to be unfrozen, right, by setting the freeze-based network to false. What this does is this modifies the weights and biases in the existing neural, the pre-trained model that we have taken up. So the ResNet 18 version 1 that we take up, what this will do is this flag will unset the weights and biases and they'll also be learned. Now we've also compared. So as you can see, when we try to take a frozen network versus when we unfreeze the base model, and the model pretty much learns it much more and much better than, not much better, minutely better as compared to a frozen network. However, if you also look at the training time, training the entire set of weights and biases versus training just the final layer, there is a difference in time, which is pretty obvious. Here is a plot of training accuracy for both the experiments. With the unfrozen network, you have a constant improvement in accuracy. There is also a validation accuracy plot. As you can see, the unfrozen network has better training and validation accuracy. In fact, we not just have the options of freezing or unfreezing the entire network, we have the option of freezing and unfreezing certain layers or selected layers from the network. So for example, if a network has suppose 30 layers, 30 convolution layers within the architecture, you can just choose to unfreeze the first 20 layers to be trained. And this selection, what it does is it gives you the freedom to tweak the model much better, and ultimately land upon an architecture and a set of weights and biases that function perfectly for your use cases. How we can do so? So in the first option, we've chosen to freeze the entire network, right? However, with the update freeze layers flag, we can pass in an integer value. So when you set the data set, within the summary, you get a list of potentially trainable layers and the number of layers that you are actually training. So in the model details section, you can also get this using the summary function or when you load the data set. So within the model details, you can find the number of potentially trainable layers that you can set this value to and the number of layers you are actually training in this experiment. So since we have frozen the model, what we are doing is we are only training the final layer and none of the layers for ResNet. However, as soon as we update the number of layers to be trained, we have updated the number of trainable layers here. So the number of weights and biases for 22 convolution layers will be trained. And we can keep varying this, modifying this as and when, tweaking this depending on what kind of accuracies we get. we can keep pausing and resuming our experiments so that we ultimately land up on the best set of hyperparameters we need. I'll just quickly go back and import our library so that we can continue our experiment. Right. So let's import our functions. So now that we have checked what freezing and unfreezing means, let's look into the last two model parameters that are available to our access. Right. So during training, when we are experimenting or prototyping an experiment, it usually would happen that the pre-trained neural network that we've chosen might not suffice or might not be complex enough to learn the tasks that we are building. So, for example, in our case, where we are building a dogs versus cats classifier, uh, for people who've already experienced and built MS classification projects, you would understand that even mobile nets would be complex enough to learn such a simple problem of differentiating between cats and dogs. However, if you complicate the problem and maybe try to differentiate between natural imagery and natural scenes, mobile nets or maybe using JOLOs would not be complex enough as neural network architectures to learn the differentiating parameters or differentiating factors between the images. And so we might have to use more complex deep learning models. However, you cannot answer this just by stating that a model is complex or not. You would actually have to check and evaluate whether a pre-trained model works with your data set or not. So to do this, to keep on switching between different pre-trained neural architectures and finding which one fits the best, you can do so dynamically. So we choose a pre-trained network as resnet 18. Having done so, even without having to train, and if you realize that resnet is something that you do not want to use, and you would rather switch to dense nets and train for 5 epochs, you can do so. Finally, evaluate your model. However, don't forget, after updating any of the model or the hyperparameters, ensure that you reload the network so that all these state changes and flag changes are saved in the project. Again, you can check out the available list of pre-trained models using the list_models function. Lastly, you can in fact also modify the pre-trained model that you're trying to build. So this was one of the first steps that we built in transfer learning. So adding a custom layer to a pre-trained neural network that has to be trained and defining the shape of that final layer that we wish to be trained. So how can you do so? We'll check into the details of how you can do this better and build your own custom neural networks soon. However, before that, so you see there is your resnet structure available to you. What you can, however, do is you can list available layers. So you can add either a linear layer final, as the final layer before the output layer, or a dropout layer too. You also have available activation functions that can be appended in the end. So here what we have done is we've added a linear layer with 1024 neurons, an activation layer with the ReLU function, a dropout layer with a probability of 0.1, and we have appended a final linear layer, setting the final layer flag as true. Now, this is something that you can do to append a final layer to your pre-trained neural network. This usually helps you build a scalable neural network architecture. So usually pre-trained models come with their own set of weights and biases that are tuned to a specific task. However, if you're trying to achieve something entirely different from the task that the pre-trained model was built for, you can add custom linear layers or dropout layers and different activation functions to tweak the pre-trained model to the custom tasks that you are building. So for example, you're taking a pre-trained model that was trained on natural images and tweaking it for the purpose of classifying, say, medical imagery. A couple of things that you would do is you would unfreeze the entire pre-trained network, and you would also add a couple of layers, final layers to tune the tune the neural architecture to your custom use case. Not to forget that after modifying any of the model parameters or hyperparameters, reload the experiment. Now, as you see, there is a final layer attached to it with the shape that we mentioned, and you can train this the same way you have been doing so. So these are the available model parameters within MonkAI. We'll move on to data parameters. Before that, let's go back to our experiment once. Let's try building this. So we've created our project and experiment, and we decided to choose DenseNet 1-to-1 as our neural network model. We've also set the number of epochs to 5 in our case. So as you can see, the running this default function prints some summary about the project, so which includes the dataset details. So where is your image dataset stored? Some of the dataset parameters. So what is the input size? What is the batch size being processed? The number of processors in use, and the training validation split. All of these can be changed, and we'll look at how to change some of these. It also prints the available number of images, both in the training set and the validation set. It lists the available transforms that have been applied. It describes the model parameters in play. So it is not using GPU currently. It is using the pre-trained network, and it has frozen the pre-trained base network. So we are not training the pre-trained neural architecture. We are just training the final layer. So in the final layer, there are 2 final layers that are being trained, whereas there are 243 available layers that can be trained. So DenseNet is a pretty deep neural architecture that can be trained and tweaked for different purposes. We also have a list of optimizers, learning rates, and loss functions that are in place here. So this summary can be accessed later on too, using the summary function. And you get access to the same pieces of information. Next, what we can do is we can run the training process, and we'll wait till the training process is completed. In fact, let's go back and check out some of the data parameters accessible to us that can be tweaked. In fact, before I move on to the data parameters, I would like to take a gap and discuss in case anyone has any doubts or queries. Abhishek?
Sure. I would request everyone to post all their issues as well as any troubles they are facing on the comment section.
All right. So let's continue. I hope anyone who's following the notebook live and the experiment live is able to do so. In case you're running into any hassles or any errors, feel free to comment in the comment section, and we'll take a look. Abhishek, if you can make my screen in the presenter section. Thank you. Yeah. So going back, we have the training process running. Let's check out some of the available data parameters that we can modify and update. Now, the first step that usually you would like to do is change the batch sizes to speed up the the training process. Usually, when working with powerful compute systems with heavy RAM or GPU memory available, you would want to do so so that a larger batch size is processed in every iteration. Doing so is very simple. Again, after having imported the library, creating your project, uh, and setting your dataset path. So as you can see, in this case, what we have used is we have used a CSV labeled dataset. So here we passed a folder of images, the part to the folder of images. This images folder would contain all the images individually as files, no folders. And there is also a train labels.csv file. The CSV file, what it stores is basically an ID or file names and the labels of each file name. Like described earlier, currently we just support single label image classification. Multi-label image classification is in works, and you'll see that pretty soon. So right after you've created your experiment and passed in the data set, you can use the update batch size flag to pass in the number, the batch size that you want. Now, this batch size depends on the available RAM or the compute memory that you have, the GPU or the RAM memory. So usually when playing around with this, it might just so happen that at times you would have set this value to a higher number, say 64, and your RAM does not support those many images concurrently in the memory. And when that happens, the training will crash, and you would have to later on update the batch size to a suitable number that can be stored. Now the batch size also depends on the image dimensions that you have set earlier, right? Because the total memory that passes on to that your system can store at one go is limited. So it depends on together both the batch size and the image dimensions in use. Again, not forgetting to mention, after updating any of the model or the data parameters, do not forget to run a reload. So because if you don't run a reload, the flags or the parameter values will not be updated. Next is shuffling training data before training. Now, this is usually done to ensure that not the same set of data is passed every time, which basically would mean a very overfitted system because it has been seeing the same set of images over and over for the same number of epochs. So shuffling data, what it does is it randomizes the set of images that are passed in each batch so that your model sees different imagery and does not overfit. How can you enable shuffle data? Well, again, very simple. To update or enable shuffle data, you set the update shuffle data flag to true and run a reload. So all these fall under the data parameters. Before this, we were checking the model parameters that entail whether you want to freeze a network or whether you want to use a GPU or a CPU or if you want to add a new layer. These metrics of setting the data shape, the batch sizes fall into the data parameters. Next, we can change the number of processors processing the data. So depending on the number of CPU cores that are available to you, you can update the number of processors running, running the training process. Again, it's pretty obvious, and we've tried to ensure that they are the flags and the parameters are pretty obvious and are related to the jargons usually used in the deep learning world, so that you don't have to hunt anything. All this is also mentioned in the readmes and the process files, and in fact also described beautifully in the Jupyter notebooks itself if you go through them once. Coming on to managing your train and validation splits. Well, one of the strategies that every deep learning engineer learns, when they are beginning with their exposure to this field is managing a train validation split or a train test split, right? You can update your train validation split using, again, the flag known as update train val split, and you can set the percentage. Now, the percentage here means this is the percentage of validation data, sorry, training data. The value mentioned here, or the percentage mentioned here, is the amount of training data that you want to use. And so 1 minus this will be the value or the size of the validation data. So as you can see, we have a warning mentioned here that you should ideally keep your training data greater than 50%. And as you see, the number of training images versus the number of validation images has updated. Again, to set your train val split to 50%, you can do so by passing in a float value, as you see. Next, so this is one of the features that could be put to some interesting use cases, specifically for continuous learning. So this feature that is available within Monk is the change dataset feature. So for example, if you've created a project and a new experiment and are working with some data sets, say for example, malaria data set, right? And you are using a part of that data set for the current experiment. What you can ideally do is, after having explored with a smaller data set, you can push in another data set, an entirely new data set. So for example, if you trained your model on, so say, data set A for malaria classification, and in the meanwhile, you also gathered a data set B, which has a similar annotation structure and a similar dataset format, but an entirely new dataset for malarial cells. What you can do is you can update your existing experiment, or in fact, ideally copy from your existing experiment, update the dataset path to ingest the new dataset that you gathered, the dataset B, reload your experiment and train on that. Now, this ideally was built for a couple of use cases. One being that you keep on gathering more data set and you want to keep on updating your project to be applied to apply your training process to a newer available data set, maybe larger or maybe a brand new unknown data set that you might have captured. The second thing that this also helps in is the process of continuous learning. So for example, you're trying to build an image classification system, and initially you just had a data set of 5,000 images for the set of objects that you were trying to classify, and slowly moving ahead, you gathered, say, 50,000 images over a period of time, and you now want to train your experiment on these 50,000 images. What you can do ideally is you can copy your previous experiment, update the dataset path, and train a new model on this new dataset, while keeping the weights and biases that were learned from the previous experiment, so that you do not lose the features learned during that experiment. In fact, there are a lot of there are a couple of competitions going on that target image classification for different different poses of objects. So a single object which appears in multiple different poses can be learned using this continuous learning method, and hopefully we'd love to see some cool applications coming up from some of the audience members today. Lastly, we have some data transformations available that can be applied to your input data set. So by default, certain horizontal, vertical flips and normalizations are applied. You can remove all the default transformations that are applied and in fact apply your own. So as you can see by default, so as soon as you load the data set, you get a list of applied transforms that are already in place for you, right? So you have your random horizontal flip with a probability of 0.8. So there is a 0.8% chance that the input image within the batch will be flipped horizontally. There is also vertical flip or normalization and other transformation functions accessible. So to reset the transforms and remove any of the applied transforms, what you can do is you can run a reset transforms. So when you run reset transforms, what it does is it removes all the existing transformations that have been applied. So right after this step, there will be no transforms that are applied to your data set. Now again, just like checking out the available models, you can check out the available transform within MonkAI by using the list transforms function. So as you can see, you have random resize crop, a center crop, color jitter, random lighting, resizing, and normalization available as transformation functions. Different now, not to forget, and just to mention here, different backend. So Pytorch, Mxnet, and Keras. So different backends would have different available pre-trained models, different transformations, different loss and activation functions available to you. So don't forget to check out the list of available models, transforms, and losses that you can play around with. So as you can see, you can apply different transformations to your data set, from normalization to center cropping. And lastly, very important, just after applying any kind of transformation or updating any of the hyperparameters, do not forget to reload your experiment. So I guess that was it for the data parameters. Let's just check our experiment, how that went. So as we can see, the experiment ended with the best validation accuracy at 53%. Not very good, of course, given that this was just trained for 5 epochs and it was a dense net model that requires a lot of training, and we just trained the final 2 layers rather than the entire network. Next, what we can do is let's check out some inference. You can find the workspace folder within your working directory, which is right here, right? Within your workspace folder, there'll be a project folder, and within your project folder, there'll be your multiple experiments. Now, to infer, what we do is we load our experiment in eval-infer evaluation mode. So what this does is it sets the training flag to false. So it basically tells the system that we are not training this time. Just to check out some of the outputs that are generated and some of the logs. As you can see, there is a training validation loss curves that are stored. There is also a model performance that is stored. So just to check out the training loss curves, as you can see, there is a training and validation loss curve stored within the experiment folder. There is also your final trained model. So as you can see, for every epoch, there is an intermediate model that is generated and stored. You can set, we'll look at how to not do this because this consumes a lot of memory. You have your best performing model and the final model that was generated after the 5th epoch. So your best performing model could come from, say, the 3rd or the 4th epoch in our case, maybe because maybe the validation accuracy was the least for the 4th epoch and not the 5th epoch. However, the final model that is generated, it is generated after training for 5 epochs entirely. Now that we have loaded our experiment in inference mode, we can load a folder of images on which we want to evaluate. So this eval folder, this cats and dogs eval folder, what it would contain is two folder of images, one with cat images and one folder with dog images. So as you can see, there are 50 images available in this folder, which are divided into two classes. So you can evaluate on a folder of images, which is something that Kaggle or HackerEarth competitors usually have to do running before they can prepare their submission CSVs. So let's run our accuracy. Until that time, let's check out some of the training parameters. Before we move on, again interrupting, in case anyone has any doubts, please feel free to share in the comment section. I guess things are going good in the comment section too. No active queries as of yet. All right, so I'll move on. All right, so let's check out some of Abhishek. If you can just set my screen to go live. Thank you. Thanks. All right, let's check out some of the training parameters that are available, at our leisure. So the training parameters being updating the number of epochs, whether we want to display the accuracies after every iteration or after every epoch, whether we want to print the pretty print messages that are sent from the backend, and also whether we want to save the intermediate models or not. Let's check out some of these. So as we've seen, when at the step where we call the default function, we can set the number of epochs at this very step right after creating our experiment, wherein we pass the dataset path and choose the model. We can set the number of epochs right here. However, after having created an experiment, if we want to update the number of epochs, we can do so too. So right after creating loading the dataset, you can update the number of epochs by using the update num epochs function and pass in an integer value mentioning the number of epochs you want to train. Again, reload the experiment after updating your parameters, and you can resume training for 15 epochs rather than 5. Now, if you compare experiments, validation accuracy remains the same. However, you can see that the training time has tripled from 5 to 15 epochs. The training time has pretty much tripled. Also, one more thing that you would observe in this case when you are training for 5 versus 15 epochs. So experiments that you train for lesser number of epochs, their endpoint would be somewhere around, would happen before the other experiment. So for the experiment that ran for 5 epochs, it ended somewhere here. Now, since we have shuffling enabled for our training process, you can see there is a minor difference in how the model went about learning. However, it ultimately did converge to after 5 epochs. The 15 epoch experiment ran longer and has better accuracy, as must be obvious. Again, as we can see, for validation accuracy, of course, this would be different, since both the models in both the experiments would be seeing a different set of images because shuffling is enabled. So the performance of the validation accuracies in both the cases would be different. Right. Having updated the number of epochs, you can update whether you want to display all that's being print. So if if you want to run training without having to print all those messages. So for example, if you're running a training process as a backend background script, and you just want very basic output messages rather than the entire print message, or in fact, in case you're running the training process as an API in the background and you do not want a lot of logging to be communicated between the client and the server, you can set the display progress real time to be false, and a lot of printing messages that are generated during the training process are skipped off. So when you do so, when you set the update display progress to false, all it does is it just sends the final, it just communicates when the training started and when the training ended. And finally, once the training ends, it provides you with certain values like where was the final model stored and where is the logging directory. Next, so when you are usually prototyping or experimenting, for lesser number of epochs, you would not ideally want to save intermediate models. So for example, if you're training for 5 epochs, you would not want to save intermediate models. However, in case you're training for 100 epochs, you would ideally want intermediate models to be saved even though there is a pause and resume capability available with Monk. You would still want to maybe evaluate, say, after 20 epochs, how well your model performs on a test data set. So you would want to enable, saving intermediate models when training for longer number of epochs, but not for quick prototyping, of course. So you can disable saving intermediate models by setting the update save intermediate models flag to false. This is again a Boolean flag, and you can set this to false. And this will not save any of the intermediate models that were generated. Only the final, the best, and the resume models are saved in this case. And finally, again, reload the experiment right after you update any of the parameters. So those are the three parameters that are available to tweak the training process. Finally, we have a list of hyperparameters that are accessible for developers to update, namely the three hyperparameters: the optimizer functions, the losses, and the learning rate schedulers that can be varied for each experiment. Before we go on to checking the hyperparameters available and how we can update, let's look at our experiment. So as you can see, when we run an evaluate sorry, when we run an evaluate function, it provides you some cool insights into your model performance. So it provides you class-based accuracy for individual classes. So we can see that the model has learned about the cat class very accurately, very nicely. So whenever we input a cat image, it can distinguish between, it can determine whether it's a cat or not pretty confidently. However, for the case of dogs, it cannot determine whether the input image is dog or not that confidently. As you can see, the performance is just 8% accurate. So you can see that the cat class was trained pretty nicely, but the dog class wasn't. So maybe adding more images to the dog class might help, or maybe unfreezing the base layer or training for more epochs could help. Any of the multiple strategies available to deep learning engineers could be applied here and could ultimately lead to improvement of performance. However, that's left to the developer. You can go back home, try out different approaches, see how you can improve. I believe someone in the comments mentioned that they got 86% accuracy. Well, try and achieve that. Apart from inferring on a batch of images or a folder of images, so apart from evaluating on your validation set, which is already labeled, you can also evaluate or infer on a single test image. So again, what we'll do is we'll load our experiment. So I guess our experiment is already loaded. We load our experiment as in inference mode. Since our experiment is already loaded, we don't have to do that. We get an image. I guess this happened because oh, sorry, apologize. I did not update the name of the project and the experiment. Do so in your case in case you have updated your experiment and project name. So just to mention a disclaimer here, at times when you're running your experiment on Colab, Colab might take a wee bit longer than it usually would take on your local laptops or local systems. Do not mind that. It just so happens that in the background, some processes are running and the files are being loaded. And since Colab file loading is a bit slow, it takes a little bit of time to load the experiment and load the files, specifically on Colab. This usually does not happen on Kaggle. So Kaggle has limited the number of GPU hours for developers. Coming back, since we have loaded our experiment, let's infer on one single test image. And as we mentioned, our model is pretty confident and is successfully able to distinguish cat images and determine whether the input image is of a cat or not. So in our case, it's 86% confident that the input images it is seeing is of a cat. Let's check out another image of a dog. Now, as you can see, like we described, that the class-based accuracy for dog is very bad right now. And that is pretty much evident from this inference result. As we can see that when we input a dog image, it confidently states that it is confident that it's seeing a cat with 98% confidence, which is pretty flawed, and the model would definitely need improvement. So some of the insights that are provided at different places helps are pretty intuitive for developers to improve their performance, their model performance as they go on. All right, let's get back to some of the hyperparameters that are available to developers. So to begin with, we start with the optimizer function. The optimizer function, I hope within deep learning everyone understands that backpropagation or any learning algorithm, the goal is to optimize the error function or the loss function that with deep learning. And optimizers play a very big role in how the model goes about learning the task that it is set to. Now, that being said, there are a lot of different strategies of applying different optimizer functions to different use cases. There are specific optimizer functions for specific domains and use cases that you can look into. So in MonkAI, let's look into how to set optimizer functions within MonkAI itself. So right after setting your loading data set, setting your number of epochs, choosing the pre-trained neural network that you want to use, by default, every experiment has stochastic gradient descent as the optimizer function setup. The default learning rate is set to 0.01 with no momentum or weight decay. If you get into the depths of how the optimizer function works, you would find out that these are some of the controlling parameters or the control knobs of the optimizer that you can tune, right? So from the learning rate to the momentum of how fast it goes about changing the learning rate, to the weight decays, to moment dampening rate, to clip norms and clip values. If you get into the depths of how an optimizer function works, you would get to know and understand how each of these knobs would control and in what way would each of these knobs control the optimizer function. That being said, different optimizer functions would have different knobs and you would have to go through each of them individually. Now, to see a list of available optimizers within MonkAI, you can just use simple list optimizers function, and it tells you some of the available optimizer functions that you can utilize. Now, the optimizer function is usually initialized with a learning rate, an initial learning rate that you want to start out with. and you can pass these other features if needed. So just to mention that, for entry level developers, you can begin with just setting the learning rate to a value that you find is suitable and is applied for your use case. However, for expert developers, there are these features that or parameters that are also accessible to you that can be modified for your experiment. So moving on to the loss functions that are available. Loss functions is something that is optimized for every experiment or every use case. If you look at how machine learning or deep learning is applied, actually, and in fact the maths of it. So again, very similar to how you updated your optimizers. By default, softmax cross entropy is the loss function that is set. You can update and find out available loss functions using list losses. You have L1, L2 loss functions. You have softmax cross entropy or just cross entropy. You have sigmoid binary cross entropy and other such loss functions. Also, not to forget, I would like to mention that different backends would have again different optimizers, loss functions, regularizers, and learning rate schedulers available for you. So don't forget, when you're experimenting with different backends, Mxnet, Pytorch, and Keras, just check out the different available optimizers, loss functions, and schedulers that are accessible to you, and play around with them. So you can reset your loss function from softmax cross entropy to an L1 loss, setting your learning rate, and finally, do not forget to reload your experiment after updating your hyperparameters. And right after you have updated any of the transformation functions or the optimizers or the loss or any of the model or data parameters, you can continue your workflow in pretty much the same manner. You can continue with a training or the update value, howsoever you like, in the same fashion as you've been doing so, as listed in the experiments. So you can connect a lot of multiple of these transformations together to create a single experiment, and then evaluate how the transformations or the tuning of knobs that you've done has impacted the performance of your model. Finally, we have learning rate schedulers. Well, so for audience members who do not understand what this would do, what this does is, as you train for more number of iterations, you wouldn't want to keep learning a lot or shifting your weights and biases by a large margin. So you keep on changing the delta with which you update your weights and biases to a smaller number as you move on. So for example, for the first epoch, you might be using 0.01 as your learning rate, which is the multiplying factor with which your weights and biases are updated after every epoch or every complete pass of your data set. However, after say the 50th or the 100th epoch, you wouldn't want to shift your weights and biases by a lot, by a big margin, because intuitively your model might have learned certain things about the data set. So you would want to now move on into slower steps of weight and bias update. So you keep on reducing your learning rate, and learning rate schedulers is something that helps you do this. So as you can see, there are other knobs or other parameters that can again be updated here, like gamma functions or the last epoch that where you want to update. So there is a step size function. The step size for step LR. By default, a step-based learning rate scheduler is applied. What this does is, after fixed number of steps or fixed number of iterations, it reduces the learning rate by a certain value. Right? There are other learning rate schedulers available too. So you have a fixed learning rate wherein the learning rate remains fixed throughout the experiment. You have a step degrees and you have a multi-step degrees. I think that's the available hyperparameters. I would request all the audience members to go back home, just check out once how they can, tweak multiple hyperparameters, connect them together in an experiment, and how that impacts their, performance, computer vision model performance. Some of the extra features that are available within Monk is one of the features was mentioned yesterday too, which is training time. So you usually do not want to, start out an experiment and then find out that it's going to take another 20 hours for the experiment to complete. So we have a small minor function available within at our leisure, with which you can estimate how much training time would it take for a given number of epochs. So if you pass any value n to this, any integer value n to the number of epochs variable, it would give you an estimate of tentatively how much time would it take to train for that many epochs. You can do so right after loading your data set. So after having chosen your pre-trained network and your data set, right after this, you can start estimating the number of, the training time for a given number of epochs. Apart from this, we have a basic EDA for image dataset, specifically for image classification. So a lot of times, working with competition dataset, it usually happens that there are a few missing images or corrupt images or images for which labels are missing. Pandas does handle this pretty neatly. However, we have some pretty print functions available for you. And even doing that with the default EDA, doing that with pandas is still a hassle because you still have to go through a lot of things. Loading the CSV file, loading the images, looping through the entire folders before you find out whether you have any corrupt images or not, or if there are any missing images. So with MonkAI, as soon as you pass the dataset path, your EDA can be prepared. So EDA has a few options available, so you can check if any of the images are missing, and it will let you know whether there are any available images or mention images that were corrupt or missing, and it will list down the file names that were corrupted or missing from the data set, so that you can either remove those files altogether from the labels file or from the directory completely. Now, to begin with, what we were running live was the quick prototyping mode. We do have an expert mode available at our hands too. So these expert mode tutorial notebooks, what they've done is they've combined all the features and the parameters that we looked at right now and prepared a singular workflow wherein you can update the loss functions, the pre-trained models, you can apply different transformations. You can set all the three, the data, the model, and the hyperparameters all together in this single notebook. You can also append layers, append dropouts and activation functions. You can update your training parameters right here, updating your optimizers, setting your loss functions, and carrying out the training process. In the quick mode, you had access to pretty much just the basic options that should be accessible to entry-level developers. However, with expert mode, you get an explained workflow of how to go about tweaking certain values in a sequence. And again, not forgetting to mention, after running any of the updates, please do not forget to run a reload in the end. I hope everyone has been following till now. We'll be moving on to how we can build custom neural networks with MonkAI and some of the available notebooks that you definitely should go through, and some of the custom building blocks, neural building blocks that are available within MonkAI that you can use directly. Some of the state-of-the-art neural networks that are available as custom, custom neural network development toolkits. So we'll go over some of these. Let's maybe take a couple of minutes break. Hopefully you guys would want to take a break, I feel. And we'll answer any queries that the audience members has right now.
Yeah, so Jaswant is asking, generally one can use time it and try, and Ved is asking about what's the logic or the algo used to identify the training time. So it's basically more on the end of how we do it is we take the entire training suite and run a simple experiment with lesser data set as well as lower epochs. So we have a function in Monk that takes the entire data set, subsamples it into 2% of 3% of data set, and then we extrapolate the entire work. And Ganesh has a question on, are there any limitations for building the neural network, the custom neural network? I don't think there are any restricted limitations as of now. The only limitation that could come in would be the number of layers, but we have made sure that all the layers that are existing in Pytorch, Keras, TensorFlow, Mxnet, they are existent in our Monk. And soon we'll also be adding the newer layers that do not exist in these native frameworks. Like group convolution is one of them that we are working on.
Hello everyone. Limitations for building neural networks using MonkAI. Well, Ganesh, just to mention before, I hope Abhishek got a chance to answer everything. We'll be looking into how we can create custom neural networks and discuss some of the constraints that are there within the library, and hopefully that would also clear out some of the doubts. So in fact, let's move on to how we can build custom neural networks with MonkAI. So let me share the screen. Abhishek, can you make my screen go live? Thank you. Yeah. So within the getting started roadmap, you have tutorials on custom network builder. Um, this was one of the most fun experiments to develop. Uh, Abhishek and me had great time working on this individually, learning about graph convolutions and how probabilistic graphical models are implemented and can be implemented as an independent library, right? And something that we try to do in an intuitive and so that for developers who do not want to face a steep learning curve, we gave them an intuitive way of building a graphical model or a graphical structure, basically a deep neural network architecture. The developers can create and curate their own deep neural architectures and apply that model to different data sets. Now, to begin with, how can you do so? So you carry out the same set of steps. You set up the Monk library. You import whatever backend you want to work with. So in this case, it's Gluon, right? And you set up your experiment. You load the data sets. Now here you can see some of the advanced parameters in place. So we are updating the train validation split. We are updating the input size. We have updated the batch size and the number of processor. We have set the shuffle data to true. All these can be done in one single step. We apply some transformations to the data set and we load the data set. After having done so, we can begin. So as you can see in the default, in the dataset parameters, we did not load a pre-trained model. So in our case, we are setting the data parameters and not running the default function directly. So right after creating the experiment, what we did was we set some of the dataset parameters that we wanted in place. We applied certain transformations and then we ran the load dataset function. This function loads the dataset into memory. After having done so, we begin by defining what our neural network would be. So if you look at broadly what is accessible to developers, there are namely convolution layers, normalization, activation, and loss layers available to developers. Now, if you look at how we go about building one, you start by initializing an empty network, of course, and then you keep on appending different types of layers as and when required. So step one is appending a convolution layer with a dimension of or with an output channel of 64. Next, you add a normalization layer to this very convolution layer, and finally an activation function relu to this block. Now, what this does is this forms a block of convolution. This forms one block of convolution rather that processes your data one by one. And if you look at one of the major hassles that developers have to face is managing the shapes or the dimension of these layers, and having to work out the mathematics of it. How one shape, a shape of m cross n would fit in with the shape of p cross q, and matching these two together is something that is usually hassle for developers. In fact, what we've done is we've rather eradicated or removed that step from the developer's part. So a developer, all they have to do is mention the number of nodes within each layer, and the shapes are automatically debugged and allocated. So after designing your complete network, so after adding one more convolution layer, normalization and activation function, and finally adding a pooling layer to the second convolution block, you run a debug function. What the debug function does is it connects each of these mentioned layers in sequence. It connects and also creates an input and the final output layer for you. So as you can see, there is, you start out with the data. Your network starts from here. You've added a convolution, a batch normalization, and a ReLU layer here. Next, in the second part, you have convolution 2, batch normalization 2, and ReLU 2. And finally, you have one pooling layer available at the end. which is pretty much your base structure for the neural network that you were designing. Moving on, you can keep on doing so. You can keep adding depth to your neural network and keep repeating this, so that you have a single flow of data, singular graphical flow of data across each of the nodes and each of the operations. You can keep increasing the number of nodes, nodes available in each layer, and the shape. So for this layer, which is shaped at 128 nodes, and this layer shaped at 64 nodes, both of them get connected automatically, so that you don't have to do any hassling job of determining what shape what shape or how many number of nodes do you want to ensure in each layer. That is automatically done by Monk in the background. Finally, you can also add a flattened layer, dropouts, a fully connected layer with these many units. And finally, as the final layer, what you have to do is you have to pass in the number of output probabilities that you want to generate, right? So for example, if you have a dogs and cats classifier, you ideally want to output just two probabilities: a probability of whether the input image is a cat or a dog, and whichever is greater. So the output layer has to store the number of classes, or the number of specifically in cases of transfer learning. So you set the final layer or the output layer as the number of classes, the number of nodes in the final layer as the number of classes, sorry. And you finally, after appending or adding any layer, you run a debug custom model design function. What this does is, so that after adding any layer or any block, this automatically connects each of those layers, determines the shape of each layer, and connects the data layer to the sequence of nodes and layers that you've added. Finally, once you have defined the shape and have ultimately defined the final layer of the model, you can run a compile network, and wherein you pass the network that you created. So we initialized an empty layer, if you recall. We started out with an empty network, and we kept on appending different layers. We kept on appending different activation functions and normalization and pooling. And finally, to compile the network, we pass in the data shape. So we have an RGB imagery, so the 3 channels, along with the input height and width of the image, and the network that we want to connect it with. So this compile network would create your final custom model that you designed yourself, with different number of nodes in each layers. This can be considered a deep neural network too. So this is the default visualization that comes with Monk. You can use Netron, a very cool library for visualizing your custom neural network. So for Netron, you still have to pass the data shape, and you get a pretty visualization of your custom neural network that you design on your own. So you see the shape of each individual layer is managed automatically and set automatically, so that you don't have to go through the hassles of debugging. Continuing, once you have created your network, your custom neural network, you can continue with the training process. You can train this neural network again. So apologies. So like we mentioned, we aren't using the default route here. What we've done is we set our dataset parameters earlier separately rather than loading them with default. We began by setting up some of the dataset parameters that we saw earlier today. Then we defined our custom neural network. We designed our custom network. We compiled it. Next, we move on to define some of the training parameters, such as the number of epochs, whether we want to display progress or not, and whether we want to save intermediate models or not. Finally, we set the optimizer, learning rate, and the loss functions, and we can begin training. So for your custom neural network designs, you can still train your custom neural network models. Just to mention one thing, the model described here, or the model designed here, it wasn't designed for any specific prototype. So for example, if you were using Gluon prototype or Pytorch or Keras for that matter, the neural network that you defined here, the custom neural architecture that you defined here, can be used with different backends altogether. So you can switch your backend framework to Pytorch and still use this custom neural network design to train your model. Now this was a pretty simple, straightforward neural network. Let's look at how we can add some branching to our custom neural architecture. Now the steps are pretty similar to the previous workflow. We set up our library, we download and prepare our data set, we import the library, set our backend, again Gluon. We create our project and experiment. We begin by initializing some of the dataset parameters that we have to store. So for dataset split, input dimensions, batch sizes, shuffling data, and the number of processes, along with the dataset path that we want to utilize. We apply transformations and dataset. And finally, coming on to creating a custom model. So again, you start out with an empty network. You start by appending convolution layers, normalization, activation functions, poolings, and your your neural architecture structure looks something like this. So if you look at the data flow, data starts out at this point, at the data point, moves on to from one layer to another sequentially, right? However, to add a subnetwork to this straight neural network, you create another subnetwork, empty subnetwork. You add multiple branches to this subnetwork. So again, you create branch 1 with its own convolution, normalization, and layers. You create 3 such branches, 3 different branches. And what you do is you append the subnetwork at this point, at a concatenation point. So to append and concatenate subnetworks at a point, you append the 3 branches together. So after creating subnetworks and 3 branches, you append the branches to a subnetwork, and then finally concatenate the subnetwork to the main network. So what this does is, after having created this structure, these many convolution and pooling layers, activation layers and 1 pooling layer, what we've done is, after this pooling, we've added 3 branches. So one is an identity layer, one is a convolution layer, and the other block contains 2 convolution layers altogether. Now, when data flows, it flows sequentially up to the pooling layer point, after which it branches out into these 3 branches. And the computation of all these 3 branches ultimately gets concatenated at this point. You can further go on building or adding more layers, convolution layers or pooling layers after the concatenation point. So you can resume designing your neural network just as you were doing so earlier. And after every component or every sub network that you design, just run a debug custom model design, so that the shapes and all the node values and the node numbers are determined by the network. Again, to create a subnetwork at suppose this point. So if you've designed your network up to this point and you want to add branching at after this point, you can do so by creating a subnetwork, an empty subnetwork, defining the branches that should exist within the subnetwork after that point, append the branches in the subnetwork, and add the subnetwork to the main branch. Right. And again, similarly, after adding any component, any blocks to the main network, just run a debug custom model design, which adds the actual shapes and the number of nodes to the model. So we have had branching at 2 points in our neural network, and defined the final layer here in the end, right? So our final layer again has the number of classes as the number of output nodes. And finally, we debug the model design to generate a final, to debug our final model design and set the number of nodes and the layer shapes. Finally, after having debugged the design that we've just created, we run a compile network with the network design that we just did above and the data shape. So an RGB image with 2 to 4 width and height. When you compile your network, you get to see the number of potential trainable layers that your model has and the number of layers you would be training if you run train right now. Again, you can visualize your custom model using Netron. This visualizes your neural network or custom neural network with the available number of nodes and the shapes of each layer and how branching is happening in each of the layers and where they get concatenated. Again, after having set the dataset parameters and designed the custom neural network, you can set your training parameters here with the number of epochs and display progress and save intermediate model flags as true or false. Lastly, you set your optimizer, your learning rate, and the loss functions, and you can begin your training process. I hope everyone has been following till now, and in case of any doubts, I hope Abhishek has been helping you out. And moving on to some of the interesting parts of how this custom network designer helps deep learning engineers and computer vision engineers. So finally, when we have the capability, and since we have the capability of designing custom neural networks, what we did was go on and implement state-of-the-art neural network architectures into Monk itself. So if you go into study roadmaps and image processing deep learning roadmap, you will find different building blocks or deep learning building blocks that are very state-of-the-art. What these deep learning building blocks are, in fact, are custom state-of-the-art neural network architectures implemented using MonkAI. Now, what you can do with these is you can pick up ready-to-use deep learning building blocks, connect multiple of them together to create and curate your own custom neural network that is humongous in shape and size, and evaluate whether creating complex and convoluted neural architecture helps learn the problem that you're tackling right now. So if you go into the image processing deep learning roadmap and the deep learning advanced roadmap and check out some of the deep learning blocks available, you'll find state-of-the-art deep learning building blocks having been designed and implemented and already accessible to you. So let's check out one example. For our case, let's check out a SqueezeNet fire block. So SqueezeNet excitations have recently come up and become very popular since they achieve a lot of accuracies and they are also fast. So the primary structure of a SqueezeNet network is this. So and the notebooks that we've prepared are pretty self-explanatory. So you don't have to refer to any other resources. In fact, we have added any external resources that you would like to go through and gain more information. So here we start describing the layers in each of the branches and what are the different layers available within the model. So as you can see, there are 2 branches. There is a common layer. What does branch 1 contain? What does branch 2 contain? And when does concatenation happen? So what we do is, since we know the structure of this building block, we start about by implementing this model using MonkAI. We create each of the branches and append each of the sub branches into the main network, and finally compile the network so that we finally have the SqueezeNet building block, deep learning building block available to us. Just like any other deep learning framework, you can initialize random data and pass it through the graph network and see how that modifies or how data passes correctly or whether data passes correctly or not. You can visualize the model architecture with Netron 2 again. And once you've defined your network, your custom network, you can directly access it using some of the predefined building blocks that we've made. So if you look at some of the available blocks, you have Inception, DenseNet, ResNets, And most of the state-of-the-art deep learning building blocks available as ready to use building blocks. So when you are designing your own custom neural network, you can pick up an inception or a squeeze-net fire block readily directly from one of our predefined building blocks. You can set the number of pre-trained parameters that it takes, so the branches that it has. So branch one has these many nodes, the squeeze channel has these many parameters, and once you import this, you can still move on to add more layers to this, appending your own layers, layers or pooling layers or loss functions to it, and finally compile your own custom network. So you can play around with state-of-the-art neural network architectures, tweak them and find out if you can improve performance on some of the state-of-the-art data sets. And you can not just do so with one backend, but all the three backends. So all the state-of-the-art deep learning building blocks are accessible from all three backends. So you can use them with Mxnet, Pytorch, or Keras. It's immaterial of the backend. We have added certain study links where you can learn more about what and where this deep learning building block is applied or used, and why it is used. What are some of the USPs, both mathematically and practically, when using or applying this building block. So you can check out some of those in the researches. In our building block notebooks, what we've also done is we've stated at the end of the notebooks how these building blocks would be implemented traditionally. So if you look at how you would go about building a squeeze detection fire net, custom using default Mxnet or Pytorch or Keras frameworks, we have done so. We have added codes for the same at the end of the notebooks. At the end of, in fact, each of the notebooks. So if we check out the resnet block, so just like our previous notebook, we have implementation on all three. We have the implementation of the resnet block. We have usage details across all three backends. We have how you can go about debugging and creating your own custom and tweaking the network for your usage. And lastly, we mention and describe how you would go about implementing this network or a resnet block, sorry, in traditional Keras, Pytorch, or Mxnet. So the steps again remain the same. You start out by setting up Monk. You have a certain structure that you want to build. So the resnet block, deep learning block, has its own structure that some of the mathematical and statistical engineers defined and found out to be working. You create and define multiple branches, and finally merge and compile the network. So with MonkAI, we've tried to keep it as low-code syntax, and implemented some of these state-of-the-art deep learning building blocks that are widely used with computer vision applications specifically. So what we've ensured is we've created some of the building blocks that are state-of-the-art for computer vision and are applied specifically for transfer learning purposes. And you can, in fact, let's look at one of the more interesting notebooks where you can combine multiple such building blocks, where you can say combine inception with resnets and mobile nets together to create a single neural network of your own and try training that. So in this notebook, we try and train a mixture of blocks wherein you have resnet, testnet, mobile nets combined together into one big neural network architecture, and you try and train that. So you have set of instructions, you create your project and experiment. Again, you do not run the default function, rather you set the dataset parameters individually. You apply the transforms, and then you run the dataset function, which loads all these parameters. Next, you can find out all the available deep learning building blocks that are accessible to you. So as you can see, you have ready to use resnet, resnext, mobile net, squeeze net, and inception blocks at your leisure. So you can pick any of these building blocks. You can initialize an empty network. You can pick up these building blocks, initialize them as layers, and keep appending such layers, onto your custom neural network. And finally, compile this neural network along with, the network that you define and the data shape. So if you look at this network, this is a combination of a lot of different, resnets, densenets, and inception blocks. So you see that there's a lot of hodgepodge of convolutions and poolings and, activation functions. There's a lot of branching going on too. And finally, once you have, created an amalgamation of all these building blocks, and having compiled the network, you go on to, set the training parameters, set the number of epochs, the loss optimizer, and the learning rate scheduler functions, and finally begin to train this custom neural network that you design. And usually it would so happen that, connecting such complex building blocks would just complicate and increase the depth of your neural network, and at times you might not achieve very good performance measures, since, adding a lot of depth is like, using a sword to knit a sweater. And at times, if you use just very simple building blocks, so for example, you just create two convolution layers and add pooling, and, try to use that to tackle natural scene image classification, that would be like, using a needle in a fight, in a sword fight, because the neural network will be very simple to tackle such a complex problem. So this is something that, as deep learning engineers, you would have to, go about working towards, finding out how complex your neural network design should be to, fit or solve the problem that you're trying to tackle right now. And not just that. So lastly, just to mention once again, these custom neural networks that you build, they can be again exported as ONNX models. So they are, backend framework compatible and also inference compatible. So once you've trained your custom neural network design and trained your model, what you can do is you can export this and run inference in any of the libraries that you feel like using finally, which is, which makes the library very accessible to any developer, coming from any framework. As a final set of instructions before I leave you guys and before Abhishek jumps on to, object detection, I would request you to, just go into Monk 1, check out the study roadmap section, go into, some of the deep learning blocks that are mentioned here. For entry level developers who have, zero or no understanding of the domain of image processing, there are a set of notebooks that, go over some of the operations and mathematical operators applied in image processing, and how you can, program those mathematical operations using Python. So all you would need is exposure to basic Python programming, and you would be, these notebooks should be help you get up and running with the topics of both image processing and deep learning applied to computer vision. Finally, we keep on building such applications, such end-to-end applications, wherein you get to build end-to-end applications. So starting from a labeled data set down to, training a good enough model that performs nicely on the given data set. So you have end-to-end application development, notebooks accessible to you too. So, and in fact, as a final homework that, I wish to leave our audience with. So if you go inside the study roadmaps, check out, point 2, transfer learning roadmap. In the transfer learning roadmap, you would find different notebooks detailing how modifying different parameters, so modifying different model data or the hyperparameters, affects the performance of your computer vision model. So if you want to evaluate the effect of using either pre-trained model or, unfreezing your base network and then training, you can check out these notebooks and see how that impacts your computer vision models. So you have, different model families that you can explore. You have, we have analyzed the effect of number of training epochs. So training with just 550 or 500 epochs, how does that alter the training performances? How does varying the number of classes within your data set vary the performances or the accuracy metrics? So you have all these notebooks and learning content accessible to you at and that too free of cost. So I would just request you to go back home today, try out a few of these notebooks, and in case you haven't explored the impact of some of these parameter tweaking, just check out how you can do so with Monk. And hopefully, would love to see some increase in the number of contributors that we have right now, and would love to see more hands on deck, helping us build a better toolkit. Abhishek, in case you want to take this forward and continue.
Sure, Akash. Thanks for that comprehensive explanation of all the different modules and functions that Monk already has. And hopefully, our audience has understood all the different concepts and facilities that they can use from Monk. It's already one, so I don't want to increase the time limit here. What I'll do is I'll just in a couple of minutes explain what Monk object detection already has for you.
Sure. That sounds great. That's great.
I'll just take a couple of minutes, that's it, and we can have a different session for the same, discussing object detection very specifically.
Sure.
Okay, so this is our Monk object detection library. As you can see, it has many algorithms already embedded in it, like Gluon CV fine tune, Torch Vision fine tune, MXRCNN, your very famous YOLO, CornerNet, RFBNet, and our contributors are adding algorithms for face recognition, for image segmentation on a very day-to-day basis. So very soon this will be a full-fledged library. You can go and check out all the example notebooks. There are more than 40 to 50 notebooks already present in there for you to try out and run object detection in only a few lines of code. Like here in this example, we are trying to get a trash detector that could be very useful for automated robots that can remove trash from your beaches, from your roads. So quickly just going through, we import the module, take the detector, import the dataset, insert the dataset, load the model, set the hyperparameter train. So this is the 5 to 6 line code you will find in all the notebooks, irrespective of what the framework is, irrespective of what the framework or the algorithm is. So I would request you to have a good look at these algorithms, get back to us, reach out to us on our social media platforms if you have any doubts. Soon we'll take a very good session like this on object detection. And I guess that's it from our side. Akash, do you have anything to add on this?
I don't think so. I hope the audience today got a chance to understand MonkAI's offerings, and hopefully a lot of them would try out Monk. Let us know their feedback and some of the issues that they ran into, and hopefully in the longer run, people can join us and help build some of the cool state-of-the-art features that we have in mind. Apart from that, thanks a lot. Thanks a lot, everyone, for attending this webinar. Hopefully, you got a chance to learn for at least the entry-level developers and programmers who were for whom this was a first-time exposure to image processing and computer vision. I hope you got a chance to learn something new, and hopefully, if you are interested in the topic of computer vision and image processing, and you would you are trying to apply deep learning algorithms to this domain, hopefully we would love to see a lot of you using MonkAI as your go-to toolkit when applying deep learning algorithms to computer vision. And hopefully we wish to keep on serving you, more and more as we keep on building more features, and not just in the deep learning aspect of it, but also when preparing your data set and deploying your computer vision applications in the end. So we are actively working. Our team of contributors, I highly appreciate and thank them for being an active part of this event and having answered a lot of the audience queries. And also, lastly, thanks a lot to them for helping us build the toolkit and the offerings that we have right now. Thanks a lot, guys. Thank you to the audience and GBC for organizing the event too. And that is it. Thanks a lot for.
That's it. I mean, you have summed it up very well. So let's catch up for another event next time.
Sure. Thanks a lot, guys. Thank you so much. Hope to see you safe. Stay at home, stay healthy, and keep learning. Take care, guys. Bye bye.